As an overall for today's presentation, I will start with a brief introduction about myself and about the company I'm working for, which is SMEC, and then we'll head up toward the core of the subject. My name is Abdullah Zaid. I was born and raised in Yemen, and then I moved to Malaysia to do my undergrad and postgrad studies. Then before 3 years, I moved to Australia. I have more than 11 years of experience, mainly in bridges and general structure. And I have most of my experience are really in bridges, and I have experience in highway, railway, and cycleway bridges. I've been with SMEC for about 3 years. I've started with SMEC Malaysia for a couple of months, then I've moved to Sydney. This is just a picture about my country, Yemen, and this is the capital city, Sana'a. SMEC stands for Snowy Mountain Engineering Corporation. It's attributed mainly to Snowy Mountain Hydroelectric Scheme project, which is one of the engineering wonders. In 2016, Surbana Jurong acquired 100% of SMEC Group, and SMEC together with Surbana Jurong are highly ranked among the international design firm and global design firms. A list from the engineering news record. Few of the latest awards and accreditation received by SMEC are listed, and what we embrace in SMEC is our culture. I mean, since I joined SMEC, I felt really welcomed by everyone. And one of the recent projects we have completed is Sydney Metro Northwest on the picture here. And this project has won various awards. The presentation scope will start with an overall introduction about load rating and why we need the load rating for bridges. And then I will go to the case study of a bridge we have done in SMEC. I will explain the bridge details and how is the bridge current condition and how did we do the modeling, and a brief overview of the results, and we will finalize our presentation. The objective of today's presentation mainly, and what everyone expects to gain from today's webinar, is understanding of the levels of bridge investigations, and then how we undertake the load rating and the fatigue assessment. Why we need to undertake or to do load rating? Generally, we have aging structures. Some of the structures in Australia and around the globe have been built last century or the century before. So it has been like more than 100 years. And with the development we are going through, there are a lot of demand for increased loading as well. So like given the Sydney Harbour Bridge was built in 1932, which now it's 88 years. Definitely the trucks that used to exist in 88 are different than the one we see in the streets today. And there are a few occasions around the globe where bridge collapse has happened due to overloading. And in this picture, you can see a bridge collapse in India. And it's also important from the asset management point of view to make the asset management more efficient. The difficulties we experience with old bridges is sometimes we don't have a date for a bridge. When was this bridge built or designed? Because an early estimation of how good is the bridge is when was it built and what codes the bridge were built to. So that will give us a first estimate of what sort of loading can go through that bridge. And also the availability of the drawings. Some bridges we don't have even, we don't have drawings for them. I'm quite interested on the old hand sketches and the simplicity of the drawings for, earlier engineers, which probably will have only a few drawings for a bridge. But the problem sometimes we can't have those drawings. And also from the fatigue perspective, we need the loading history for the bridge, and we will get into details later. Bridge assessment standards. We have in every country or in different continents and countries, they have different codes, but in Australia, we have the overarching code AS5100, which is used nationwide. And we have different parts, and part 7 is especially for bridge assessment. And then we have a state and client requirements as well. So each state in Australia has its own guidelines on how we undertake the bridge assessment. In New South Wales, that's where Sydney is, we have, for example, the ASA or the Asset Standard Authority, that's which gives us a guidelines of how we undertake the bridge assessment. And other states like Victoria and Queensland and other states as well, they have different guidelines and manuals. In general, there are overarching steps for the bridge assessment, which is also given on the AS5100, part 7. But in general, we have levels of assessment, which is basically level 1, 2, and 3. And level 1 is mainly to check the general serviceability of the structure and identify any emerging problems. Then we have level 2, which is a bit more comprehensive visual inspection. And in level 2, we will do a specific rate, to rate the condition of each component of the bridge. Then we have level 3, which is a detailed engineering investigation. This includes field investigation and also a structural analysis. That's where the load ratings come. The fatigue assessment is also in level 3, and fatigue is an interest topic, and especially for steel bridges. And then we have the rehabilitation and strengthening. So from the flow chart on the right-hand side, we can see the steps that we generally follow for the bridge assessment. We start with data collection. That's to look whether we have drawings or previous condition assessment of the bridge. And that's also for the Assets Authority, for them to identify the number of assets and the location of the assets as well. Then we have the bridge condition, which tell us whether the bridge is in a good or poor condition. Then we have the field geometry. That's especially if it's an old bridge, sometimes we don't have a drawing, as I mentioned before, or sometimes there have been a lot of modification to the bridge. So we need to take that into consideration when we do the bridge assessment. Then we move to the capacity assessment. That's basically take the individual component of the bridge and calculate how much are their capacity. After that, with modeling and analysis, we undertake the analysis to find out the load effects and the load factors. Then we have the fatigue assessment. And after that, after we finish all that, the bridge assessment and load rating will be done via an equation given in the code. If the bridge has an adequate capacity, then when we finalize the assessment, but if it is not, then we have to undertake either like a higher tier assessment, if that's an advantageous, like nonlinear analysis or a specific and site investigation and load testing. And then if that's fine and the capacity could be validated, then it's fine. But if it is not, then we have to impose sometimes some restrictions on the bridges. Why we need to do this bridge assessment? It's effective for asset management perspective. So we reduce overstressing of the structures. So we maintain the reliability and the life cycle of them. And it's ultimately it's more safer and for the safety of the users. And it helps also to reduce the cost of maintenance. Load rating. So when we undertake the load rating, we have different steps as well. So we start with the as new load rating. Basically, the as new load rating is the design load of the bridge with regards to the as-built drawing. So this is assuming the bridge just built, and based on the drawing, what is the capacity of this bridge? Then we have to undertake the structure mapping and condition assessment. This is basically to identify any deficiency on the existing bridge, like suction losses or cracks and spalling of concrete. And if there is also from the structure mapping perspective, if there is any new members or strengthening of the bridge, or maybe some additional structure to the bridge itself, so that's we have to undertake that in our assessment as well. Then we have, after the as new load rating, we have the as is load rating. So this, when we undertake the as is load rating, it's basically to illustrate how much capacity has the bridge lost during its lifetime. So that could be due to the corrosion or any other external impacts. And then after that, we undertake the fatigue assessment. Basically, the fatigue assessment, the bridge could sustain the load from the ultimate limit state point of view, but the fatigue assessment has a limited life for the bridge components or members. And we need to check, based on the loading history, how much of that fatigue life has passed and what is the residual remaining life of the bridge. The fatigue assessment or the fatigue analysis has gained a bit of interest, and it's mainly because there have been few bridge failures, especially steel bridges. And the reason is attributed to the fatigue. That's why we have heard about bridge, or we have experienced a bridge failure for bridges that lived for 50 and 80 years, and they collapse at the end. So there are different reasons for that, and one of them is the fatigue loading. So to give you an overview of the fatigue, basically when we design a bridge to ultimate limit state, we will just see how much is the ultimate strength of the section, and we can load that section to its ultimate capacity. Nothing will happen. But if that stress or that load has been repeated 100,000 times or millions times, then as we see, the fatigue capacity will reduce with the increase of the load cycles. So for instance, if we have a stress of sigma A1 that in a structure or in a bridge, so for that stress, we can only load the bridge in 1 cycle's time. So if this N1 is 1,000,000 cycles, so we can have that stress to run 1,000,000 times. But if we expect the bridge to have more than 1,000,000 cycle, then we have to reduce the stress by increasing the section. And this is very important. This analysis is very important for fatigue sensitive structures like the sign structure or the highway sign structures, and also for the bridges. And we can see the more cycles we have, the lower stress need to be designed for. And from this bridge from this graph from the literature, it has a cutoff limit, but based on the recent code AS5100 2017, this cutoff limit seems to be disappearing. So previously, we believe that if the stress is low, we can have unlimited number of cycles, but from the new code, that still accounts. Even the low stresses still accounts. Even it's an algorithmic like relationship, but it still accounts and it still contribute to the damage. So we will get into the bridge details. So basically, this U-through bridge is a rail bridge, and we call it in Australia as steel under bridge. Basically, it's been differentiated between the underbridge and overbridge. The underbridge is basically any bridge that carries rail, and the overbridge is for bridges that carries roads. The bridge was built in 1914, which gave 106 years. And the span is heavily skewed in 27 degrees, as we can see from the plan. That's where the apartment is. And this type of structure is U-through girder. It has, the span is 25 meters and the width is 8.2, and the substructure is masonry abutment. Basically, the U-through girder or the U-through bridges consists of main girders or the through girders, and then we have a cross girder, which I will show you the picture in the following slide. So this is the bridge outside. There are 3 bridges with the same dimensions. The main girder, it has 2 main girders, as we can see, and the U-through girder advantage is to minimize the structural depth, because most of the structural depth, as we can see from the photo on the left, is above the rail level. So it maximizes the clearance underneath the bridge. The main girder is 2.5 meters deep. It varies because we have like more plates at the center of the bridge or the center of the span, but it's about 2.5 meters. The cross girder depth is 0.85 meters, and the stringers is between 355 to 500 millimeter. So this mainly the internal stringers, and the end stringers are deeper because they are longer, as we seen here. So those stringers are longer. We have the transoms, as we can see from this picture. They are a timber, and we have the cross bracings, which are like equal angle structure, and then we have connections. Basically, that's what connect or riveting the cross girder to the main girder and the stringers to the cross girder. So as I have explained, what is the parts that making the bridge, or what are the components of the bridge itself. But there have been like questions of what we need to model and whether we need to model everything. So from engineering judgment, the engineer should have the ability to judge and model the things that affect the structure behavior. So it's not the interest of modeling everything, because with the advanced softwares we have, like MIDAS, we can model everything on the bridge, like cross bracing, the connections, and the rivets and everything. So it's like whether we need to go to that depth or not. So I've illustrated that with 2 types of modeling. We have the grillage model and FEM model. The grillage is simple line models, but the FEM models is more into like plates and 3-dimension modeling of each component, or such as the webs and the flanges with the stiffeners and the connection. This model is done by one of my colleagues in SMEC as well. So what I have modeled mainly, or what's been modeled in the grillage, is the main girders, the cross girders, the stringers, and the transoms, just to transfer the load. And then cross bracings, because they are mainly for stability, we haven't modeled them, and also the connection for the basic model were not modeled. The bridge condition. So we have typical issues with steel bridges, like corrosion, as we can see. This is like a corrosion in the top flange of the stringers, and this is also the bottom flange of the stringers around the abutment. And also we have seen some missing bolts as well. Then for the bridge condition, we have undertaken a structural mapping. Basically, the structural mapping scope is to identify any old members being replaced, or any new members that has been used to strengthen the bridge. Also, any strengthened elements, like as we can see in this member, this is a stringer with a welded additional plate on the web. And also a change for the section capacity, where we have losses on the top flange, bottom flange, or the web. We have to identify those and estimate how much is the capacity after the section losses. So it's also important for us, after doing the condition assessment, to think whether the changes happens to the bridge. Do we need really to remodel the bridge and use the new sections or the new members or not? So this has to happen in case-to-case basis. If the element will change the stiffness of the bridge, we would need to rerun the analysis. But if it is only contributing to the section capacity, we might not need to remodel and reanalyze the model or the bridge. That's what happened on our bridge. So from this structural mapping, we can see some of the stringers has been replaced, and also some of the cross bracings as well. And we have also, as I've shown in this picture, we have additional plates to the webs. So coming to the bridge modeling. So the type of analysis we use is basically a linear modeling for longitudinal analysis. What is the purpose of that analysis is to obtain the forces for different load types, and mainly for moving loads. And we have then to calculate the fatigue stresses via the time history analysis, which is a bit interesting part of this bridge scope and this presentation as well. And then after that, we have to calculate the section capacity of the structure members, so then we can do the load rating. So how we model the bridge, basically, we have created sections for all the components, which are the main girder, the cross girder, and we have the stringers. So as we can see in this screenshot from the MIDAS model, we have 3 main girder sections, because we have different depth of, additional plates at the center of the bridge, as I mentioned before. And it's illustrated here also on the cross girder as well. So we can see it's a riveted built-up section. We have a section where it's only single flange, top flange and bottom flange toward the end. Then it goes to 2 blades riveted. Then it goes to 3 blades. So that's why we have 3 sections for the same cross girder. We can see also the stringer and how it's connected to the cross girder, and also we can see the connection between the main girder and the cross girder, which are via this riveted connection. So how we define the section? The section has been defined with the coordinates, defined by coordinates, and that's where we could input all the coordinates for the top flange, the web, and the bottom flange, calculating the effective area, which it's very useful. There are different ways to model the bridge and the sections, which is an advantage with MIDAS. You can model things, whether it's in a CAD, then transfer it, or you can build up your model, your sections, and model on the MIDAS itself. So the boundary condition. So we have bearings at the end, and also we have the connection, which needs to be modeled also. And that's where we define the support reaction based on the bearing from the drawings and also at the site inspection. And then we have the beam end releases, because as we can see in the connection, it's not really a fixed connection with top flanges connected, fully connected to the web or to the main girder. So there is some releases of the bending moment. It's also at the stringers as well. It's being considered as a pin connection while it's only through the web. The web is connected to the member. If the connection has a top flange connection as well, it will transfer the moment as well. So the boundary condition, basically we have a roller bearings at one side and fixed bearing at the other side. And we have a sliding bearing for the stringers. So we can see that's the main girder, and we have two supports. One will be fixed and the other roller. And that's one main girder, and this is the second. Yeah. Let's see. Okay, so this is the first main girder, and that is the second one. And then we have, these are just the stringers connected to the cross girder, and we can see also the green circles around this area, which is the moment release, or the end releases that apply to the moment, or to the members, sorry. Okay, we need to get rid of, I'll just leave them. So what type of loadings we have used? So we have, dead load, superimposed dead load, and we have the live loads, which is the moving loads we applied on the bridge, and then we have the wind load. So for the live load, we have different type of moving loads, which is the 300 LA, is basically the train loads, or the heaviest train loads in the code. Then we have the Warata electric, is basically the passenger trains, and we have some freight trains and other loads identified by the client. For the fatigue assessment, we would need to undertake a specific loading arrangement. So we have to apply not idealized maximum loadings of the bridge, but rather the actual loading that been traveling on the bridge itself. So this has a specific load arrangement, and we will come to it in a second. So the types of live load, as we can see from the code, we have the 300 LA rail traffic, which is defined here, and we have the Warata electric, which is also given, like this is just a single car, and in this picture I'm showing the trains that we use in Sydney. They are double-story trains with what we call a water-dielectric. And from the historic, for the time or for the fatigue assessment, we needed the historical data. So from the real resource center or from the historical data of the trains that traveled that bridge, we managed to identify 9 types of trains, and these trains has different arrangement. This arrangement is crucial for identifying the stress ranges and the number of cycles for the bridge. This is very important when we undertake the fatigue assessment. And I will cover the fatigue assessment in a minute. So we have 9 types of loading or specific loading that has been traveling that bridge, and apart from the load rating for standard rail loading. The time history analysis, basically, on MIDAS, when we run the moving load, we will get, the MIDAS will run an influence line method, which will give us the maximum forces. This will give us the maximum moments, shear force, torsion for each member. And from the live load tracer, we can see which load has caused that maximum loading. But the issue with the fatigue assessment, we are not looking at one single result or the maximum loading. Rather, we are looking at the fluctuation of stresses when a moving load is applied. This is where it's become very important for us to undertake the time history analysis. MIDAS provide that. It was designed originally or mainly for a seismic loading, but it's been useful also for tracking the historical loading from a moving load as well. There is a specific training of how we use the time history analysis for moving load to identify the stress fluctuation on a single element as a moving load bus. And this training will be on next week, 11th of June, and it's available on MIDAS Academy, and this is a link for registration as well. Coming back to this graph, just a bit of stress history for end cross girder. So as we can see, there is 3 graphs and for 3 types of trains. And what we need to look at for the fatigue assessment, we would need a stress cycle, and then we need also we consider like the range of the stress. For example, in this orange colored, the range is between 0 and 45. It's about 45 MBA. That's the stress range, and we need to calculate how many stresses, how many cycles, like 1, 2, 3, 4, 5, 6. There is 6 cycles of around 45 MBA. Then with this number of cycles and stress range, we can then calculate how much is the fatigue damage, what is the actual fatigue damage to the structural element. So then basically from the results of the load rating, we can extract, as I mentioned, the maximum forces for bending moment and shear force. This is the global model with the bending moment diagram, and it's as a result from the 300 LA loading. And it's quite useful in MIDAS how we can extract the results, whether it's like in a table format or a graphical format as well. This is a graphical format for the main girder with the loads shown on this legend, and also for the internal cross girder we can see the bending moment diagram as well. For the shear force is similar we have, this is the shear force for the main girder, and also the cross girder is shown in this diagram. This is the stresses from the historical loads, the historical load stress from the time history analysis. This is what we will extract for the fatigue assessment. We will have the loadings or the stresses. This is for the shear force, and that's for the bending stress at a specific location on the bridge. So this will help us to calculate this stress cycle ranges and we will do the count. Basically, the code gives us two methods to do the count of the stresses. Basically, it's based on either like the reservoir method or the rain flow method. And this is a different topic which needs a different probably seminar or webinar to go through how we calculate that. There are many references available online how we do the cycle counts for a moving load. Now we come to the load rating factor. So we have calculated now, when we modeled, we know what is the design effects, and we have checked the member capacities. We calculated the member capacities. Then we will be able to use this formula from the AS5100 to do the load rating, or as they call it, rating factor. The rating factor will give us, if we are checking like a 20-ton vehicle, we'll be able to check if the rating factor, if it is above 1, then this bridge can accommodate the 20-ton vehicle. But if it is the rating factor is below 1, then we have to limit the weight on the bridge. So from the section capacity we have done. In this table, I'm giving just a summary of the bridge components, and then we can see the results for the as new capacity and as is capacity. So as I've explained earlier, we have the as new capacity assuming the bridge just built, and this is the ultimate capacity that the bridge can take, but the as is considering all the corrosion happens and the impact on the structure. So we can see most of the elements has a reduced capacity from the corrosion. Rating factors. So this is a summary for the rating factor for one load case, which is the Warata Electric, 2 tracks loaded. So we can, that's how the code define it, or how the local authority define it, how they want the results to be presented. We have to show the bridge component, which is different, like the through girder, cross girders, and the stringers. Then what design actions we are checking. This is the dynamic load allowance, and then we have the as new rating factor, and then the as is rating factor. So as long as all those factors above 1 is fine, but as we can see in this, the end stringer has a capacity or loading rating factor below 1. So this is marginally below 1, which needs further investigation as well. And here are the results for the fatigue residual life. Basically, what we have done specifically for this bridge, the client asked us to undertake the fatigue assessment based on 2 codes, the 2017, which is the recent copy of the AS5100, and also the 2004 copy of the AS5100. So we have undertaken those 2 just for understanding how the changes in the code affects the results. So from the analysis we have undertaken, we found out the end cross girder and the intermediate cross girder has exceeded their fatigue life. But considering the 2017 code, and it's approximately 3.6 years of loading will bring it to, the full fatigue damage, or the full fatigue damage for the end cross girder for 2004 issue of the code. We don't have to do that for every bridge, but because we just, I mean, when we got this project, we were transferring from 2004 to 2017, and it was an interest for the client to understand how the changing the code will change the results. So as a conclusion for the bridge analysis itself, so we have found more that the bridge required more detailed investigation because there were some deficiencies, not only in the Warata Electric, not only in this load case, other load cases has resulted in some deficiencies, and that's why we needed to undertake a more detailed assessment, and we went for nonlinear assessment as well, nonlinear analysis of that bridge. And also for the fatigue, the cross girders are critical for fatigue analysis as well. So they need to have more investigation, which is a fracture mechanic investigation for the cross girders as well. So overall, to summarize our webinar, we started the bridge analysis or the bridge assessment with data collection, where we got all the drawings. Then we have done the bridge condition assessment. After that, we verified everything from the field, the field geometry, and we I mean with the condition assessment and the structure mapping. After that, we went for the capacity assessment of the bridge with load rating and fatigue. And what we found from the results using the rating factor that there is no adequate capacity, so we needed to do a higher tier assessment, which went for nonlinear analysis. And now, I mean, after that, when we finalize this analysis, we will go to the final conclusion, whether we will restrict the loading or we will strengthen the elements. We will get to any questions that you have in this seminar, and we will try to answer them. And the answer will be provided through MIDAS to everyone, to all the attendees. And that will be uploaded together with this webinar online on the MIDAS Academy. Thank you everyone for attending this seminar, and look forward to see you on the next seminar for the time history analysis for this bridge as well. Thank you.
Hi, Abdullah.
Yeah.
Did you turn off the screen?
Yes, I did.
Because there are some couple of questions from the audience.
Okay. Is it? I can see only one. So you want to show the screen? Will it extracting the results?
Maybe it's better because people might think it is over. One question from one of audience. How do you determine the number of cycles in fatigue analysis? This is from line 10 Chi.
Sorry, what is the question?
How do you determine the number of cycles in fatigue analysis?
Okay, the number of cycles, as we explained. Okay, so I will just go back to this. As I explained, the cycle counts has to be undertaken by reservoir method or rain flow method. So we have for each moving load, we have different cycles, as we can see from this graph for the bending moment, or let me go to the previous graph, which is clearer. So this is how we calculate. Basically, the reservoir method will tell us, based on the train 2, which is the orange graph, we have 6 cycles of 45 MBA. Then we have also to calculate those small cycles, and that has to echo for each loading and each train. Then after that, from the authority, they will tell us this train, how many times it passed on that bridge for its lifetime. If it is, for example, 100,000 passes, then we multiply this total number of cycles by the number of passes, and we will get a total number.
Okay, thank you for the answer. Next question is how to check connection details like rivet and bolt in assessment.
There's, and in the code, they are giving us some guidance onto how we calculate the connection capacity. We have different methods. We can carry out like a special analysis for that, but there is a simplified methods where we just take the web connection for the shear and the top and the bottom flange for the bending. But if that didn't work, we have to take the group to analyze the group of the bolts, and using the vector analysis of the groups, that will give us how much each rivet or each bolt is taking in terms of forces.
Okay, thank you. Next question, Dr. Jade, please explain if I'm seeing warping in the conclusion slide upper right model. Was there any model on the conclusion
Which
slide?
one? Yeah.
Maybe, I think so.
Yeah. What is the question? Sorry again.
Please explain if I am seeing warping in the model.
This is just it's not. It's just a nonlinear analysis where we determine the effective length of the main girder. So it's not really a warping. It's a distortion. You can see it now is exaggerated just from the analysis point of view, but nothing happens on the bridge itself.
Okay, thank you. And next question, is any instrumentation done to assess the fatigue life?
I didn't get that. What is the
instrumentation?
Instrumentation, yeah. There will be, if the calculation or if the theoretical calculation have found that the bridge has exceeded its fatigue life, there will be a site inspection or where we will measure if there is any cracking, fatigue cracking happens to this the bridge, and those cracking, there is special instrumentation to take them, and from those cracking they will identify how much fatigue has occurred to that section, and that's what we call the fracture mechanic type of analysis. So there is, yeah.
Okay, thank you. And other, what about fatigue assessment of connection? Was that carried out? Was a detailed model carried out for the connections?
Yes, we have undertaken also the fatigue assessment for the connection, which gives us how much the stresses on the bolts itself and the fluctuation of the stresses in the bolts or rivets in this case has been reported as well.
Thank you. And is the higher tier analysis compulsory requirement by the code or regulation? One can go ahead to limit the loading acceptable to the bridge, or recommend retrofitting without the higher tier analysis? Do you understand the question?
Yeah, I will try to explain what is the stages we take it. If the adequacy, if the bridge has no adequate capacity, it depends. If it is really well beyond this, the section, the bridge capacity, we will try to limit the loads in the bridge. But if it is within some like percentage, which will be able, if we can reduce the dynamic load impact, or as like reducing the speed of the trains, in this case, will reduce the dynamic load impact, and that will help, then we will undertake that. And for the higher tier assessment also, sometimes we need to validate something from nonlinear perspective as well, because that will give us a better results.
Here's another similar question from the previous question. Also, any instrumentation done to measure the actual stresses on the bridge?
We haven't gone to that analysis yet. This project is ongoing, and it's still, we might need to do that on one stage if it is found necessary.
Here's a similar question. Are sensors built into the bridge component for stress assessment? Maybe it is the same answer.
Yeah, the same answer.
And another, which software is used for FE analysis?
It's also MIDAS FEM analysis. We have undertaken that. No, MIDAS Civil, yes.
Okay. There's another question. Thank you, Abdullah. Very insightful seminar indeed. I was wondering if you can explain more on how you project load cycles for the future loads.
Based on the code, it's quite hard to anticipate what the loading cycles, especially for road bridges. But for rail bridges, the authority will tell us if they will have a capacity to increase, like freight train and passenger train, and if it is on planning. But if it is not on planning, we will just we will assume the similar loadings for the last year, and that's what the code told us as well. We will just use the last year, and we will assume that's the number of cycles will continue similar to the last year, unless there is a specific requirement by the client and telling us, oh, maybe the frequency of trains will increase by this amount, so we can anticipate how much is the damage as well.
Okay, thank you. And why not derailment load and temperature stresses were not considered for this bridge assessment?
For the derailment load, this bridge was built and designed before 100 years. So definitely it can't stand the derailment loads or the impact load of the current code. That's why we can see from this picture, we have some derailment rails being implemented, but it's not within the scope of our analysis. Temperature change will induce some stresses. For simply supported bridges, it's not that critical.
Okay, thank you. Here's another. Hello, Jared. In full finite element analysis, how do you determine failure of the bridge? In the UK, we check buckling curves and development of plastic hinges.
Sorry, what's the question again? How
I'll read again.
Yeah, please.
In the full finite element analysis, how do you determine failure of the bridge? In the UK, we check buckling curves and development of plastic hinges.
It's similar. I think there is a similarity of that. Usually, the buckling length will determine to us the main girder capacity, because the capacity, the cross-section capacity or the member capacity is dependent on how long is that element. And on this one, that's why we undertaken the nonlinear analysis to identify what is the actual buckling length of the bridge. And we found that the buckling length from the nonlinear analysis was quite, I mean, less than the theoretical buckling length, which is the spacing between the cross girders.
So is it a nonlinear material analysis rather than linear finite element analysis?
Yeah. Originally, when we did for the first tier analysis, we just done it based on the theoretical calculation from the code, but then we validated that with the nonlinear analysis. That's what we could see on this graph. This is basically to identify how much is the buckling length of the main girder.
Okay, thank you. Can you also highlight specific differences between the 2004 and 2017 versions of the AS code?
For the fatigue assessment, the graphs has been changed. The formulas also have been changed. There is, I think, it's beyond the seminar, because I haven't created the comparison here. But what I can recall, there is a change on the formula type and the factors within the formula itself, and also, as I've shown in previous graph, let me just go back to that graph. The cutoff limits from the previous codes has been removed in the new code. Yeah, so this graph has changed, which is the fatigue strength curves has changed from the previous graph to the new graph. Previously, we had a cutoff limit. If anything, like if any stress below that cutoff limit is not accounted for, but on this new code, we have to account, I mean, the damage from also a small fatigue stresses as well.
Okay, and also I think it is hard to specify every differences between the codes here. Next question, can you please speak about whether the constant or variable amplitude method should be used?
I think that will be explained on the upcoming seminar, and I think this is for the time history analysis. The upcoming seminar will give more in depth of that analysis as well for the time history.
I'm actually didn't understand about amplitude method.
I think if I'm not mistaken, the constant of variable amplitude is from the time history analysis, we have it. I don't know whether I understood that question or not.
I'm not sure neither. Anyway, let's go ahead with the next question. Do we need to use another software for connection? How do you think of this question?
I mean, there are a variety of softwares. I have some like spreadsheets which I use for my connections, and where we have some problems with the connections, we need to model them, and we try to calculate the capacity, or it depends about whether we are considering only the plastic or the elastic or the plastic capacity of the connection. But whether it's like this software or different software, it has to be modeled right.
Yeah, I agree. There are a bunch of methods to analyze the connection. If it is like a simple beam model, we can use MIDAS. If it is solid or plate model, we can still use MIDAS. But if somebody wants to check like the capacity of the connection, maybe that kind of automation, we need to use other software maybe. Am I right?
Yeah. Yes.
Yeah. Okay. And if there is no in situ test, are you assuming that each element is up to its full capacity?
I didn't get that. If no, was it in situ?
If you didn't check every like a correlation of each member, when you analyze the model, are you assuming it has a full capacity without any damages?
For the as new assessment, we assume it's the full capacity, but for the as is condition, we have to calculate any appreciable losses of the section or losses of the capacity. So the final answer will be determined based on the as-is capacity, but the idea of calculating both the as-is and the as-new is sometimes if the loading is beyond the as-new capacity, so we need to strengthen the section anyhow. But if it is between those, then we can undertake more detailed analysis for that section as well.
So you mean we need to like investigate the actual bridge? We need to visit the bridge and which member has damages before the analysis?
Exactly, yes.
Yes, okay. And how to incorporate corrosion of steel section into the analysis?
I think on one of the graphs I have highlighted that whether that corrosion will influence the redistribution of the stress and the stiffness of the bridge itself, then we need to remodel it. But if it is not, it just will affect the capacity calculation, and that's where we've shown it into. I mean, for this bridge, we just considered that from the capacity perspective only. So I think on this table, I'll just go to the table and the results, and that is where the corrosion, the as-is capacity, these capacities after the corrosion, and these capacities are before the corrosion.
Okay, and the rivet model is using rigid link.
He means the the FEM model.
I think in your model as well. What kind of did you use link element for rivet?
No, we've just the model. I mean, the elements has some member releases at the ends, and from those member releases, then we extracted the force and we did the connection check in spreadsheet.
Okay. Has fatigue verification been undertaken?
At site, fatigue verification is not yet, only a theoretical calculation of that.
Okay. And is there a assessment also for the masonry bearing support for MIDAS?
The bearings, you mean the masonry supports? I don't think we haven't done any load rating for the masonry inspection because it's not as straightforward. The codes are not really covering how we model and analyze the masonry structures. I know there is some softwares for masonry arches, but not for piers and or abutments.
Yeah, I'm not sure with the masonry bearings support. Yeah. Let's go to next question. Which one type of connection is suitable in terms of fatigue from load rating experience, bolted or welded?
I think Okay, when we design a new connection, we have to see how many the cycles, what is the anticipated number of cycles? And if that number of cycles are quite large, we need to see how much is the stress limit from the code. So there is a stress limit for the bolted connection and for welded connection. But I think from practice, the bolted connection will behave better because you can at any time replace the bolt easily. But if it is welded connection, then it needs a major rectification and modification at site.
Okay, thank you. We have only 2 questions more.
Okay.
The first one, how to calculate capacity of the section while doing as-is load rating?
If this, okay, let's assume you have a top flange web and a bottom flange. If the losses or the corrosion happens to the top flange, so if the top flange thickness, let's say is 20 millimeter and there's a corrosion happens about, let's say 20 or 30% of the section has lost. So we will just calculate how much is the new section capacity based on the new thickness of the top flange. So if it is 20 millimeter minus maybe 5 millimeter for the corrosion, that will give us a new section, and we will just carry on the capacity based on that assessment. So we need to calculate the net effective area, section properties and capacity.
Okay, thank you. And last question, was current rusting of the steel considered in the modeling of the bridge?
It's, I think, similar to the previous question. Not in this bridge, because rusting of the element has not changed the behavior of the bridge. It's only affected the member capacity.
Okay. Okay, thank you for today's presentation. It was very nice and useful. I think many of the audience enjoyed the presentation, today's webinar. Yeah.
Thank you very much. And looking forward the upcoming seminar, which will be delivered by you, I think.
Yeah, hopefully. Yeah.
Okay.
And
good.
I hope to plan another webinar in the future with you.
Thank you very much. Yeah.
Okay. Thank you, everyone. Thank you for joining today's webinar. I hope you enjoyed today's presentation from Dr. Jade, and hope to see you again from the next webinar. Thank you and bye-bye.
Right.